right, so I've got steam entering a well-insulated nozzle. I've got the initial temperature, pressure, and velocity. And then, of course, I'm given the pressure and the velocity at the outlet. I'm supposed to find the rate of entropy produced per pound mass of steam flowing through that nozzle, and we're giving units of BTU per pound mass degree Rankine. I've got some assumptions there, but I'm going to kind of point out where we make those assumptions. So let's go ahead and get started. So the first thing that I need to do is apply my entropy balance for an open system. So here it is. I've got the rate of change of entropy contained within the system. That's ds dt. That guy is going to be 0 because it's steady state, equals the rate of entropy produced by heat transfer. And of course, for a nozzle, we typically assume that it operates adiabatically. And so that term becomes 0. And then all we're left with is the sigma dot, and then of course the sum of the m dot s is coming in and out. And so once I solve for sigma dot over m dot, I'm left with S2 minus S1. Now, of course, S1, I've got temperature and I've got pressure to fix my state. It ends up being superheated, as you can see from your saturated water tables A2E and A3E. And so if you go into your superheated tables in A4E, you'll see your S1 value at 1,000 degrees Fahrenheit and 500 PSI is 1.7371 BTU per pound mass degree Rankine. So now we have to find S2. So I've got pressure, that's one intensive property, but I need two independent intensive properties with which to fix my state. So I kind of think to myself, what are the intensive properties that I'm familiar with? I know pressure, temperature, internal energy, enthalpy, entropy, quality if it's applicable, and really the only thing that I can kind of easily get my hands on is the enthalpy, the H value, and I'm going to get that by applying my first law. So the dE dt guy, he's equal to 0 because it's steady state. Q dot W dot, those go away because those are typical assumptions that I make for a nozzle. The potential energy changes are negligible. That's another assumption that I typically make for a nozzle. And the m dots divide out, and so all I'm left with are the H values and the kinetic energy terms. Now, there are some unit conversions that I do have to worry about, but once I do that, I get an H2 value of 1192.325 BTU per pound mass, and so I can plug that into my equation for sigma dot over m dot to get, well, not plug that guy in, but I have to get the S2 value evaluated at P2, 14.7 PSI, and H2, 1192.325. And at P2 and H2, it ends up being superheated. So you do have to interpolate in your superheated tables, but once you do that, you can plug that S2 value into that sigma dot over m dot equation. You get a sigma dot over m dot of 0.076 BTU per pound mass degree Rankine. All right, well, I hope that was helpful. Thank you for watching, and let me know if you have any questions.